Hey guys, welcome. Yeah, so first and foremost, as always, thank you, Lord Jesus, for the blessing, man. Every bloody morning, gotta get our blessing, fam. Okay, all right. This is not rapping. And also, is it but I judge or but I judge? Speaking of judging, you, everyone, I suppose judges, because before we start the math, there was a lady in the Northeast who apparently is a Buttigieg supporter, and maybe this was on PBS NewsHour or something like that. Anyway, at the end of it, they tell her oh, you're a Buttigieg supporter, so you know he's gay. She's like, wait, I don't want that in the White House. So that's how much research the American voter does on who they vote for. Yeah, I think we should let it be known that an exit hole is an exit hole, folks. And yeah, since this channel is a little bit about starting revolutions, no, mathematical revolutions, that's all we're about. But yeah, I think people should, along with their driver's test, be given a physics test, and if they do well enough on the physics test, show understanding of centripetal force and such, they should be allowed to speed. And maybe the equivalent to that should be applied to voting, which is you take an IQ test before you vote, because maybe an uninformed voter is dangerous. No, I don't know. Let's get on with the math. It's more fun. Okay, so here are the two fun limits I'm talking about. The first one is this. Lim is x goes to 0 of 1 over x minus 1 over sine x. And this, as you'll see, is a simple exercise in L'Hopital's rule. This is why this is called L'Hopital's bonus. And this, a slightly less simple exercise in L'Hopital's rule, is the second of the two limits we're going to work on, and it is limit is x goes to infinity of its x squared times, and then its arctan. Remember, arctan is tan inverse, so arctan x minus pi over 2. So one at a time. We'll start with the one on the left, and we go to the right. Yeah, okay. Kind of like politics, left, right, left. No, okay. Yeah, and I call them two fun limits as opposed to two fun hard limits, because, well, whether or not they're hard depends on your experience. Here goes. So this first one, pretty straightforward. What we ought to do is this, which is get common denominators, right? So that amounts to multiplying by sine x over sine x here, and then over here multiplying by x over x. And that immediately gets us the common denominators desired. Okay, all right. Off grid, back on. Okay. So, in our next step then, now that we've got common denominators, we'll write limits x goes to 0 of it's sine x minus x all over x times sine x. That's the common denominator, x sine x, right? Okay. All right, so let's, as we should always, first plug in the limit point and see what happens. If we plug in 0, we're going to get sine of 0, which is 0, minus 0 over, and the bottom we get 0 times 0. Okay, needless to say, this is 0 over 0. And so remember, we can only apply L'Hopital's rule if we get 0 over 0 or infinity over infinity. These are the two determinate forms that say, okay, go ahead and execute L'Hopital's rule, although there are other indeterminate forms. But these are the two indeterminate forms that say apply L'Hopital's. That's where we're at right now. We got 0 over 0, so we can use L'Hopital's. So we go, this limit is the same as doing limit is x goes to 0 of the derivative of the numerator, that's going to be cos x, minus 1 over the derivative of the denominator. We have to use product rule here. So derivative of x is 1 times sine x, and then plus, and then it's going to be x times the derivative of sine x, which is cos x, right? Okay, cool. So now we plug in 0 in this. So since cosine of 0 is 1, we get 1 over 1 in the numerator, that's 0. And the denominator, sine of 0 is 0 still, and was, and then plus, this is 0 times, who cares, so 0. So we get 0 over 0. Buttigieg, no, okay. It's but it just rule. It's not L'Hopital's. All right. So we got to do it once more. Fine. So we got to do the derivative of this numerator now, divided by the derivative of this denominator, and evaluate the limit once more. So we go lim is x goes to 0 of the derivative of the numerator. Well, derivative of cosine x is negative sine x. So we go negative sine x, and then minus 0. The derivative of 1 is 0, right? Over. Now the derivative of sine right here. So now we're doing the derivative of the denominator is cos x, and then plus here we have to keep the product rule in mind. Derivative of x is 1, and so 1 times cos x, and then plus x times the derivative of cos x is negative sine x, so x times negative sine x. So I'll just write the negative right there. Yeah? Okay, cool. What about now? Does it work out? Well, if we plug in 0 now, in the numerator, we're going to get negative 0, which is 0, over. In the denominator, this is 1. Ah, good. Because, well, if this is 0, we're not worried. Cosine of 0 is 1. So we get 1. So another 1, and then this is 0, minus 0, who cares? All we cared is that now the denominator isn't 0, so we get 0 over 2, which is 0, and therefore the answer to this limit is 0. Yeah? Okay, cool. Now we need a little bit of space for what we're going to do over there, and over here. So let's erase here. Yeah? Okay, cool. So as always, try to plug in the limit. Technically, we cannot plug in infinity, but let us. So if we do, we're going to get infinity squared. Let's say that that's infinity. And then we're going to get arctan. And by the way, this is arctan of x squared right here. So I miswrote the original question. It's fine. I just fixed it. We never got to it until now, so it had no consequence that I forgot. Okay, anyway. Now we got to do arctan of infinity squared. What is that? Well, you need to understand how to graph arctan. This is a very, very useful knowledge. One reason is because it comes up a lot in math, right? And another reason is because the arctan function is cool. Remember, arctan is the same as tan inverse, right? Okay, so this is what the tan inverse or arctan function looks like. So it's got a horizontal asymptote right here. And you ought to know that this horizontal asymptote is at y equals negative pi over 2. It's got another horizontal asymptote right here. And this is y equals positive pi over 2. So one of the reasons why the arctan function is really cool is because it takes the entire real number line and it maps it onto the interval from negative pi over 2 to pi over 2. Yeah, so I'm saying it looks like this. And so it looks like this. Remember the tan function would have vertical asymptotes here, and it would look like this. And remember, inverses are mirrors over the line y equals x, so that alone should give you a clue as to what the arctan function has to look like. But the key takeaway here is that as x goes to infinity, arctan approaches pi over 2, and as x goes to negative infinity, arctan approaches negative pi over 2. So I'm saying arctan of infinity squared, which is arctan of infinity in this part, is going to go to pi over 2. So what we have here is pi over 2 minus pi over 2. Okay, well clearly that's 0. So what we're going to get if we try to evaluate the limit right away is we get infinity times 0. That's an indeterminate form, but that does not say that you can right away apply L'Hopital's. Remember, other than the 0 over 0 and infinity over infinity, there are other indeterminate forms like 0 to the power 0, or infinity times infinity, and 1 to the infinity, and as you see, infinity times 0 is another indeterminate form. What these other indeterminate forms are signaling is you are able to rewrite the given expression so that it becomes of the form 0 over 0 or infinity over infinity, so that you can then apply L'Hopital's rule. But these are triggers for L'Hopital's rule. You can't, based on these indeterminate forms, right away apply L'Hopital's rule. All this is to say that we are now able to rewrite this expression so that it becomes one of the two indeterminate forms that will say go ahead and do L'Hopital. And so when you have something like this, right, where you have an x to a power, the way to get to the desired indeterminate form, 0 over 0 or infinity over infinity, is to do this kind of a trick, which is lim as x goes to infinity, and then keep the arctan. I'm going to write it as tan inverse, just to like really sell the idea that arctan and tan inverse are the same. Tan inverse of x squared minus pi over 2. And then I'm gonna rewrite multiplying by x squared as dividing by 1 over x squared, because it is. I'm saying this here is the same as that, because dividing by 1 over x squared is the same as multiplying by x squared over 1. And so if you did that, if you use the interpretation that I just said, then you can get this to look like that, right? Okay, but why do I care about this? Because look at what happens now if x goes to infinity. Well, in the numerator, we're going to get pi over 2 minus pi over 2 for reasons I've already said. And the denominator, as x goes to infinity, 1 over x squared goes to 0. So we get 0 over 0. Ah, cool. So then now we can use L'Hopital's rule, because we've arrived at the, like, what is it, checkpoint that says go ahead and do L'Hopital's, the other checkpoint being infinity over infinity. Cool. And so then it goes without saying that to do L'Hopital's, we have to take the derivative of the numerator and then divide by the derivative of the denominator and evaluate the limit the same way. So we go, fine, lim as x goes to infinity. Now the derivative of the numerator is the derivative of tan inverse of 1 over, the derivative of tan inverse of x squared is 1 over 1 plus x squared times 2x. The times 2x by chain rule, right? Okay. If it was just tan inverse of x, it'd just be 1 over 1 plus x squared. And so you get it. And of course, minus 0, because the derivative of pi over 2 is 0. And then I'll have over, remember, 1 over x squared is the same as x to the negative 2. So the derivative of 1 over x squared is the same as the derivative of this. And that is minus 2x to the negative 3, which simplified would read minus 2 over x cubed. Got it. So we've got minus 2 over x cubed right here. Cool. And then we do the keep change flip, or whatever it is that you guys call it. And so we write, I don't really like mnemonics, just learn math. Why would you remember something else to remember something? Okay. Sorry, 2x over 1 plus x to the 4th. X squared is x to the 4th, right? And then dividing by this is same as multiplying by its reciprocal. So we multiply by x cubed over negative 2. Right? Yeah. And so then I could take care of this 2 right here by this 2 right there. And I could put the negative sign, like, say, right here. And this now has a denominator of 1. So I have x and x cubed. And so this is x to the 4th. And so then this is an exercise in finding horizontal asymptotes of a rational function. This is a rational function. I remember when you take the limit as x goes to infinity of a rational function, or as x goes to negative infinity, what you're really doing is you're finding horizontal asymptotes. So this is an algebra skill, but now you should see that maybe it's a little easier on the eye if I write it this way. You should see that what we have is that this limit is equal to negative 1, because we have negative x to the 4th over x to the 4th plus 1. Sending x to infinity means we're considering very large x values. So when we're considering very large x values, adding 1 to the denominator is of no significance. So this quotient is for all purposes the same as negative x to the 4th over x to the 4th. That's going to be negative 1. So this limit is negative 1, and I am done.